Greetings. Welcome to self-assessment for Lesson 8, Problem 1. In Problem 1, they ask us to fill out the following table. Intercepts must be written as ordered pairs. Always use proper notation. Round to 2 decimal places where necessary. Okay, we're going to need our calculator for a few of these problems, but the first few ones we will not. So make sure you've got that out, but let's go ahead and get after the first couple here. So the first thing they want to know is the given parabola, does it open upward or does it open downward? So we've got f of x, g of x, and y of x to take a look at there. So the thing to remember is that what we're working with generically would be f of x is equal to ax squared plus bx plus c, the function given by that quadratic function. And we know that if the leading coefficient a is greater than 0, then we have a concave up parabola. In other words, it's an upward opening parabola. If that leading coefficient is less than 0, then we know we have a concave down or a downward opening parabola. So that hopefully makes pretty short work of these first questions, because we just got to come in and investigate the leading coefficients on each of our parabolas and decide based upon those whether they open up or they open down. So in f of x we see a is greater than 0, therefore it opens up. In g of x, we see our leading coefficient is actually -1. It's not written in descending order, so we've got to be careful there to make sure we see that that's -1. So we know that one opens down. And then last but not least here, y has got a leading coefficient of 5, which is positive, so that one opens up. Okay, so the next thing they want to know from us is the vertical intercept. So the thing to recall about a vertical intercept is that a vertical intercept is the same thing as a y-intercept. So a vertical intercept is a y-intercept, and if it's a y-intercept, then what that infers to us is that x must have been equal to 0. So that tells me what I need to do to find my vertical intercepts for my three functions is evaluate them at x equals to 0. So on f, we have f of 0, which ends up being 2 times 0 squared minus 4 times 0 minus 30. So you can hopefully see rather quickly that the vertical intercept is at 0, 30. In other words, evaluate the function at 0, and what you'll find is that the output is -30, whatever the value of c was. Notice that c here is all that's going to be left standing when you put in a 0 for the x's. They're both going to drop out, right? So ax squared plus bx will drop out every time. So same song, second verse with g. If we go g of 0 is going to be 5 minus 0, which is 5. So that tells me that the ordered pair for this vertical intercept is going to be at 0 by 5. Last but not least, we've got y. When we plug 0 in for x there, looks like we get back out a 17 whenever x is equal to 0. So that tells me the ordered pair there would be 0 by 17. And that's actually also a nice little demo why most folks like function notation better, because I didn't have to write down 2 letters when I wrote using the F notation. Okay, horizontal intercepts. Horizontal intercepts a little more difficult, because now if we're talking about a horizontal intercept, then that must have meant that, switch colors here to kind of break it up a little bit. If we're doing a horizontal intercept, then that means we're talking about an x-intercept, which must have meant that y was equal to 0. In other words, the functional value, the output value, was 0. So that means we need to solve the following equations. We need to solve 0 is equal to 2x squared minus 4x minus 30. That'll be the first one we need to solve, and then we'll have to do that with g and y respectively. So let's go ahead and start off with this one. So probably the most important type of factoring you're ever going to learn how to do in any mathematics class is factoring out a greatest common factor. So let's do that on the right hand side here. So that's 2 times x squared minus 2x minus 15. And then hopefully we see pretty quickly that this factors into x minus 5 times x plus, let's see, that is a plus there, not an x plus 3. Okay, so let's check that, make sure I did that correctly. -5 times 3 gives me a -15. -5x plus 3x gives me a -2x, and x times x gives me x squared. In other words, mentally remultiply that out to make sure you got that done correctly. All right, now by the zero product property, that tells me that either x minus 5 was equal to 0 or x plus 3 was equal to 0. So it looks like my two solutions here are going to be x is equal to 5 or x is equal to -3. But be careful because they asked us to write these down as ordered pairs. We're not just going to report back those two numbers. We have to give the ordered pairs that correspond to them. So our first horizontal intercept, or x-intercept, is at 5, 0. And then our second one is at -3, 0. Okay, cool. So I'm getting a little cluttered here, so let's go ahead and make myself some room. Get all this stuff out of our way. And let's go on to g of x. Okay, so what we need to do now is solve 0 is equal to 5 minus x squared. Well, let's see, what does that say? That says that x squared is equal to 5. And by using my property of square roots, that says that if you've got x squared is equal to k, where k is greater than 0, then what we know is that x is equal to plus or minus the square root of k. So that same idea happens here, and so we get x is equal to plus or minus the square root of 5. So that tells me that my ordered pairs are going to be square root of 5 by 0, that'll be one of them, and then negative square root of 5 by 0, that'll be the other one. All right, cool. Last but not least, we've got 0 is equal to 5x squared minus 4x plus 17. Now, a couple of different ways you can approach this one. You could throw that one into the quadratic formula to solve that, or we can go and take a quick look at its graph. In other words, we can put in 5x squared, subtract 4x plus 17. Do a little bit of adjustment on window because we know that it's got a vertical intercept at 0, 17. So we don't want to, make y max 10. That's not going to do us any good. So let's set our window. Well, let's start off with the zoom and a standard just to get our window kind of where we want it. See, no graph. Oh, poor us. So let's go fix this real quick, and let's go make y max equal to, let's say, just 25. Okay, and then let's graph that. So you may pause there to check your window settings. Works for me. And what we see is that this graph has no x-intercepts. In other words, it has no real values that will cause the function to be equal to 0. So in this case, there is no x-intercepts. So there are no horizontal intercepts. So no h-intercepts, or if you wanted to say does not exist, that works also. Either of those are fine. Okay. All right, vertex. We got to go find the vertex. So if we want to find the vertex on these, we know that h is equal to minus b over 2a, and k is equal to f of h. So that's how you find the ordered pair hk, better known as the vertex. In other words, the ordered pair hk is the vertex. I know the book doesn't tend to use that notation HK, but that's predominant. You're going to see that pretty much in every other text that you're going to work forward in. So make sure you recognize that HK actually represents the vertex. So we need to know what A and B are. Okay. So on the function f, we know A was equal to 2 and B was equal to -4. So what that says is that h would be equal to minus -4 over 2 times 2, which is 2a. So that tells us that h is equal to 1. And then k is going to be equal to f of 1, which in our particular case is going to be equal to 2 times 1 squared minus 4 times 1 minus 30. And if we simplify all that arithmetic, we get back out -32. So that tells me that the ordered pair HK for the first one is going to be 1 by -32. Okay, let's get ourselves some more working space over here again, kind of getting a little cluttered. All right, so let's go take a look at find the vertex for our second find friend here. Okay, and so again, we've got, if we put this in standard order, g of x is equal to minus x squared plus 0x plus 5. That might be helpful for you to see who the value of b is if you write it like that. In other words, make it into the form ax squared plus bx plus c. So that means that b is equal to 0 and a is equal to -1, which says h is equal to minus 0 over 2 times -1, which no matter how you slice that, that's equal to 0. Okay, so what about k? Well, what's k equal to? Well, k is equal to f of 0, which in this case is g of 0. Hey, we already did that. We did that earlier. That's 5. So it turns out that there is only one x-intercept here, and the x-intercept actually is the vertex in this case. So the x-intercept is at 0, 5. So notice these two numbers are the same as these two numbers. I should say it that way, since they're ordered pairs. So what that tells us is that we have a vertex that is just sitting on top of the axes on the x-axis, and that's it. All right, let's go take a look at y, get that one done. So in the case of y, we've got y is equal to 5x squared minus 4x plus 17, which says, let's see, h was again equal to minus b over 2a. So let's see, my a in this case was 5 and my b was a -4, so that's minus -4 over a 2 times a 5, okay, which ends up, when we simplify that, ends up being 2/5. Okay, so to go find out what k is, remember k is equal to f of h, which in this case means that we have to go evaluate our function at 2/5, so that's going to be 5 times 2/5 squared minus 4 times 2/5 plus 17. Okay, so if I plug that into the calculator and ask it to turn that back into a fraction for me, I'll get back 81/5. Okay, we could round that off also if we want to, but for the moment I'm going to leave it as a fraction. I'll let you go ahead and do the rounding, because they did say we could round off to 2 decimal places, but for me, simpler just to leave it like this. Okay, so got 2/5 by 81/5 for the vertex on that one. Okay, now what about the domain? Super simple. It's a polynomial. All polynomials have the same domain. It's from -infinity to +infinity. It's what we wish everybody's domain was, but that's not true, as we will see in some of the future sections, okay, which you may have already been seeing because you may have been reviewing at this point. So you know that it's not always from -infinity to +infinity. You could also say all real numbers. You could write it in English also. That works. I prefer the interval notation. Kind of like it better. Okay, now what about range? Now range, you got to be a little more careful, because range, you got to think about whether this is an upward opening parabola, a downward opening parabola, and what the vertex was. So let's take a look at the first one. We notice that it is an upward opening parabola, so that's good to know. So we know it opens up, and we know what the vertex is. We know what those two numbers are. In other words, the 1 by -32. So knowing that, that's going to help me out, because what that tells me is that if I was to just do sort of a rough hacked out sketch here, nothing too fancy. I know it's going through 5. I know it's going through -3. I know it's going through -30 down here. And at 1, -32 is the vertex right there. And so this graph looks not quite unlike, but similar to that. Okay? And so what that tells me is that my domain goes from -infinity to +infinity. We can see that on here, but also that my range is going to start down here at -32, close dot on the y-axis, and it's going to be everything up that way. In other words, all of the y values above -32 are going to be in my range, and with the -32 included. Okay, so what that means is I'm going to start at -32, and I'm going to go up to +infinity. Now another way we could write that, kind of a simple set builder notation way, is to open up a set of y's such that y was greater than or equal to negative 32. That works also. I'll let you choose which you prefer, interval notation or the set builder notation, or sometimes referred to in our book as inequality notation. Okay, cool. So that takes care of our first function. Let's look at the next one. So if we look at the second function here and we want to know what the range of that one is, we notice it's a downward opening parabola. And so if we were to hack out a quick sketch of this, and of course you can do these on your calculator too if you'd like, but I think it's definitely worth the time and the push-up to kind of make a sketch since we've got all this information anyway. So 0, 5 we know is our vertex, and then we know we're going up, downward opening, and we're going to go through negative square root of 5 and positive square root of 5, and that our parabola is going to look not quite unlike but similar to that. Okay, so again, where are we crossing the y-axis at? We're crossing the y-axis here at 5, and so close dot on that, and we know that it's going to be all of the y values heading that way. All right, so what that tells me is that I'm going to go from negative infinity up to 5, and I'm going to stop there. Or if you prefer the set builder notation, it's a set of y's such that y is less than or equal to 5. Okay, one last parabola to take care of. That's our y parabola here, and we've got to talk about its range. So let's see. We know again this one is concave up. We know that it's going through 0, 17 on the y-axis, which is about there-ish, and we know that 2/5 by 81/5 is our vertex, which is somewhere about there-ish. So we know that this parabola looks something like this. In fact, we already looked at this one on our calculator to help us determine that it had no x-intercepts. Oh, that's a ruddy bad sketch, but that's okay. So we know that this has a range that starts at 81/5. It starts right here at 81/5 and heads up towards positive infinity. Now if you chose to put 81/5 into a decimal, that's fine, because I said we could do that out to 2 places, but I'm going to stay with the fraction if you don't mind. So that's going to be 81/5 to infinity, or the set of y's such that y is greater than or equal to 81/5. And again, you're welcome to turn that into a decimal if you'd like. Okay, axis of symmetry. Okay, so remember, we'll just use this one as grist for the mill on the axis of symmetry here. So the axis, whoops, my bad. I thought I was erasing the graph, and I'm not erasing that. So let's go ahead and start over here for just a second. We'll just give ourselves a generic version, and then we will apply that to all the rest of our functions here. So let's say we had one like our opening example here, where we had a parabola that looked not quite unlike but similar to that, okay? Where our vertex point, this point right here, we know was at 1, negative 32. Well, the axis of symmetry is the vertical line that basically slices the parabola in half. It's the line that goes through like that. Okay, and what we know is that vertical line, its equation is always going to be given by x is equal to h, where h is that number. In other words, it's the first component of the ordered pair of the vertex. So in the case of our first parabola here, that means that x equal to 1 will be our axis of symmetry, okay, or axis of evil. All right, so in other words, we have to look at the vertex, look at the first number in the vertex, set x equal to that, and that's going to give us the equation of the axis of symmetry. So that means that the next one will be given by x is equal to 0. Notice I'm just looking at that number right there. And the last one will be given by x is equal to 2/5. Or 0.4 if you want to look at it that way, but I'm fine with 2/5. Okay, well, that was quite a bit real fast. Good review of all things parabolic. If you need to, watch this one again, or you can scan through to just the things you've got confusion with. And of course, don't feel shy about sending me a message or posting something to the Q&A forum if you need additional help.